Machine learning-based compilation has changed from an obscure research niche to a mainstream research area. In this presentation, we will introduce you the topic of machine learning-based optimization in compilers and provide you a roadmap for the wide range of research areas. Compiler studies is a serious subject where correctness is very important, while machine learning is a field which deals with predictions. Yet, these two fields establish a natural research domain despite their first-glance incompatibility. The main two tasks of a compiler are translation and optimization. Machine learning predicts an outcome for a new data point based on prior data. This ability to predict based on prior information can be used to find the data point with the best outcome and is closely tied to the area of optimization. Computer architecture evolves so quickly that it's difficult to keep up. Therefore, every time the computer hardware changes, compiler writers have to come up with the best heuristic to achieve the better performance. While on the other hand, machine learning has a property of being automatic. Part 1. Machine Learning in Compilers. Overview. Optimization can be in speed, memory, or power usage. There are two main stages involved in machine learning: learning and deployment. The first stage learns the model based on training data, while the second uses the model on new unseen programs. In the learning phase, the programs should be represented in a systematic way. This representation is known as program features. The application of machine learning in compiler optimization can be divided into three main parts: feature engineering, learning a model, and deployment. Let's start with feature engineering. Machine learning relies on a set of quantifiable properties, or features, to characterize the programs. Those can be static data structures extracted from the program source code, compiler intermediate representation, such as the number of instructions or branches, dynamic profiling information, such as performance counter values. Standard machine learning algorithms work on fixed-length inputs. Therefore, features will be summarized into fixed-length feature vectors. This process of feature engineering must be done iteratively to achieve a set of high-quality features. The next step is to learn a model. For learning a model, we need to create a training data. Compiler developer will choose a program and different optimization options, and it will generate training instances with feature values and optimization options. These examples then will be fed to a machine learning algorithm to build a model. Afterwards, the model will find the correlation between feature values and compiler options. In the deployment stage, the learned model is integrated into a compiler. To make a prediction, the compiler first extracts the feature of the input program and feeds them to a model. The utmost advantage of machine learning-based optimization is that the whole process can be easily repeated whenever there is a change in hardware architecture, operating system, or application domain. Part 2. How machine learning can predict compiler optimization. One of the key challenges for compilation is to select the right code transformation, or sequence of transformations for a given program. A naive approach is to exhaustively apply each legal transformation option and then profile the program to collect the relevant performance metric. However, due to the massive number of compiler options, this approach is not applicable at scale, and its main limitation is that it only finds an optimization for a single program and cannot generalize into a compiler heuristic. There are two main approaches for solving the problem of scalably selecting compiler options that work across programs. First, Cost function to estimate the compiler decision. Second, direct prediction of the best option. Many compiler heuristics rely on a cost function to estimate the quality of a compiler option. Depending on the optimization goal, the quality metric can be execution time, the code size, or energy consumption. Traditionally, a compiler cost function is manually crafted. There is some predefined threshold to determine whether to inline a function or not, and these thresholds are defined by compiler developers. Additionally, the problem of relying on a hand-tuned heuristic is that the cost and benefit of a compiler optimization often depend on the underlying hardware. While handcrafted cost functions could be effective, manually developing one can take months or years on a single architecture. Because cost functions are important in manual tuning, a good function is difficult for each individual architecture. Researchers have investigated ways to use machine learning to automate this process. The overhead involved in searching for the optimal option in cost functions may still be prohibitive despite its advantages. Therefore, directly predicting the best decision is a promising way for relatively small compilation problems. Munzifrad and others pioneered the use of machine learning to predict the optimal compiler decision. They used a decision tree-based approach to determine whether to unroll a loop or not, relying on the number of statements and arithmetic operations in a loop. Loop unrolling is a loop transformation technique that helps to optimize the execution time of a program by reducing or removing the iterations. However, this approach only decides to unroll or not, and doesn't determine how many times the loop should be unrolled. This work was advanced and the problem was formulated as a multi-class classification problem. This approach correctly predicted in 65% of the testing loops, leading to a 5% improvement. For the sequential programs, there is extensive work in predicting the best compiler flags and code transformation options. However, it's harder for the parallel programs due to the complex interactions between the parallel programs and the underlying parallel architectures. Nonetheless, there are works on predicting the optimal number of threads to be used to run an OpenMP program, the thread coarsening parameter for OpenCL programs for GPUs.
Part 3. Machine Learning Models in Optimization. There are two main subdivisions of machine learning techniques used in compiler optimization: supervised and unsupervised learning. Supervised learning. In supervised learning, a predictive model is trained on empirical performance data, also known as labeled outputs, and features of representative programs. Depending on the nature of the outputs, the predictive model can be either a regression model for continuous outputs or a classification model for discrete outputs. Regression is a type of supervised learning. This technique has been used in predicting the program execution time input or speedup for a given input. In the illustration, you can see a simple regression-based curve-fitting example with the pink dots represented as data points. Classification is another type of supervised learning. This technique takes in a feature vector and predicts which of a set of classes the feature vector is associated with. For example, classification can be used to predict which of a set of unroll factors should be used for a given loop by taking in a feature vector that describes the characteristics of the target loop. The k-nearest neighbor algorithm is an effective classification technique. It finds the k-closest training examples to the input instance or program on the feature space. The closeness or distance is often evaluated using the Euclidean distance, but other metrics can also be used. The k-nearest neighbor algorithm has two main drawbacks. First, it must compute the distance between the input and all training data set at each prediction. This can be slow if there is a large number of training programs to be considered. Second, the algorithm itself does not learn from training data. Instead, it simply selects the k-nearest neighbors. The next classification technique is the decision tree. It has been used in choosing the parallel strategy for loop parallelization, determining the loop unroll factor, deciding the profitability of using GPU acceleration, selecting the optimal algorithm implementation. To make a prediction, we start from the root of the tree. We compare a feature value, for example the communication computation ratio of the target program, against a threshold to determine which branch of the tree to follow. And we repeat this process until we reach a leaf node where a decision will be made. The threshold is automatically determined by a machine learning algorithm, which makes it adjustable when we have different architecture or application domains. However, a significant drawback of using a single decision tree is that the model can overfit due to outliers in the training data. Random forest and ensemble learning method is therefore proposed to handle the problem of overfitting. Let's switch our topic to deep neural networks. In recent years, deep neural networks have been used in image recognition and audio processing. However, so far there is little work done of applying DNN to compiler optimization. An example of such an attempt can be DeepTune framework, which uses DNN to extract source code features. The advantage of DNN is that they can compactly represent a significantly larger set of functions than a shallow network, where each function is specialized at processing part of the input, which allows to model the complex relationship between the input and the output. Unsupervised learning. Unlike supervised learning models, which learn a correlation from the input feature values to the corresponding outputs, unsupervised learning models only take it from the input data. Clustering is an example of unsupervised learning, which groups the input data items into several subsets. The k-means clustering algorithm groups the input data into k clusters. The algorithm works by grouping data points that are close to each other on the feature space into a cluster. K-means is also used to summarize the code structures of parallel programs that benefit from similar optimization strategies. Principal component analysis is a statistical method for unsupervised learning. This method allows to reduce feature dimension, which makes it possible to model a high-dimensional feature space with a smaller number of representative values. PCA is often used to discover the common pattern in the datasets in order to help clustering exercises. Autoencoders are a recently proposed artificial neural network architecture for discovering the efficient coding of input data in an unsupervised fashion. This technique can be used in combination of a natural language model to first extract features from program source code and then find the compact representation of the source code features. Apart from supervised and unsupervised learning, we also need to mention online learning while talking about compiler optimization with ML. Evolutionary search algorithms apply principles inspired by biological evolution to find an optimal or near-optimal solutions for the target problem. In the context of iterative compilation, evolutionary algorithms can be employed. The algorithm starts from several populations of randomly chosen compiler flag settings. It compiles the program using each individual compiler flag sequence and uses a fitness function to evaluate how well a compiler flag sequence performs. The compiler settings that give faster execution time will have a higher fitness score. In the next iteration, the evolutionary algorithm generates the next populations of compiler settings via mechanisms such as reproduction and mutation among compiler flag settings. This results in a new generation of compiler flag settings, and the quality of each setting will be evaluated again. This mechanism is analogical to a natural selection process. Evolutionary algorithms are useful for exploring a large optimization space where it is infeasible to just enumerate all possible solutions. This is because an evolutionary algorithm can often converge to the most promising area in the optimization space quicker than a general search heuristic. Evolutionary algorithm typically relies on empirical evidences, such as running time, for fitness evaluation. The search time can still be prohibitively expensive. Another approach is to combine supervised learning and evolutionary algorithm by first using an offline learned model to predict the most promising areas of the design space, and then searching over the predicted areas to refine the solutions. Reinforcement learning algorithm, also known as learning from interactions, tries to learn how to maximize the rewards, or performance itself. The algorithm needs to learn for a given input what the correct output or decision to take is. This is different from supervised learning, where the correct input-output pairs are presented in the training data. In general, reinforcement learning is an intuitive and comprehensive solution for autonomous decision-making, but its performance depends on the effectiveness of the value function, which estimates the immediate reward. Choosing which modeling technique to use is non-trivial. It depends on a number of factors: the prediction problem itself, the set of features to use, the available training examples, the training and prediction overhead, and many others. More sophisticated techniques may provide greater accuracy, but they require large amounts of labeled training data, a real problem in compiler optimization. Techniques such as linear regression and decision trees require less training data compared to more advanced models such as state vector machines and artificial neural networks. Simple models typically work well when the prediction problem can be described using a feature vector that has a small number of dimensions, and when the feature vector and the prediction are linearly correlated. The more advanced techniques such as state vector machines and artificial neural networks can model both linear and non-linear problems on a higher dimensional feature space, but they often require more training data to learn an effective model. Furthermore, the performance of a state vector machine and an artificial neural network also highly depends on the hyperparameters used to train the model. The optimal hyperparameter values can be chosen by performing cross-validation on the training data. However, how to select parameters to avoid overfitting while achieving a good prediction accuracy remains an outstanding challenge. Part 4. Challenges and limitations of machine learning in compiler optimization. Training cost is an issue that many find alarming. In practice, the cost is much less than a compiler writer, and techniques such as active learning can be employed to reduce the overhead of training data generation. Gathering enough sufficient high-quality training data. Although there are numerous benchmark sites publicly available, the number of programs available is relatively sparse compared to the number that the typical compiler will encounter in its lifetime. A really fundamental problem is that if we build our optimization models based purely on empirical data, then we must guarantee that these data are correct and representative. We must learn the signal, not the noise. Peer review of a machine learning approach is difficult. Black box modeling prevents the quality of the model from being questioned, unlike handcrafted heuristics. Although the ability to automatically learn how to best optimize an application and adapt to change is a big step forward, machine learning can only learn from what is provided by the compiler writer. Machine learning can neither invent new program transformations to apply, nor derive analysis that determines whether a transformation is legal. All of this is beyond its scope.
Finally, let us recap the promising topic of machine learning in compiler optimization. Machine learning-based compilation is now a mainstream compiler research area and, over the last decade or so, has generated a large amount of academic interest and papers. Machine learning has demonstrated its utility as a means of automating compiler profitability analysis. It will continue to be used for more complex optimization problems and is likely to be the default approach to selecting compiler optimizations in the coming decade.